Hello, my name is Chejun Wan. Today I would do my project presentation, which would be reviewing two articles regarding two topics in machine learning. The two topics would be active learning and fairness in machine learning. The first paper that I want to review is Active Learning Helps Pre-trained Models Learn the Intended Task. Before I move on to the review, I would first like to briefly introduce what active machine learning is compared to conventional machine learning. In conventional machine learning, the unlabeled raw data goes through human labeling, which becomes then labeled data. The labeled data is provided to the machine learning process, and then the machine learning process learns the features and the classification details from the labeled data, which is then used to create the predictive model that can be used to classify or predict other features from other data sets. However, in active machine learning, not all unlabeled raw data becomes labeled by the human being. The raw data first goes through a special data selection algorithm, which means that the machine automatically and adaptively selects the most informative data for labeling and then provides that amount of data to the human so that it could be labeled. By this, we can minimize the amount of data that needs to be labeled to create the predictive model. We can consider this as a very effective optimization step so that the requirement of the data is minimized. The main problem that is being addressed in this article is about task ambiguity. The article provides that modern pre-trained models can be adapted to new tasks with little data, but the little amount of data can act as very critical weaknesses because the given data are often incomplete representatives of the desired behavior. This means that the given data may not be sufficient in specifying the user's intention, leaving an ambiguity in the task. For example, if we look at the figure, we give an ambiguous task of classification. In this case, the classification can be based on the color or the shape. We do not know which is correct. If there is only red squares and blue circles in the set that we want to classify, there would be no problem at all. However, if we face a new object, which would be a blue square, for instance, there would be a very big problem of classifying that object. This means that we need to remove this ambiguity in the task. This is where active learning could be used. In active learning, the machine can provide the human being, the supervisor, to label this unsure object. If the human chooses to label this with the red squares, we can then know that the classification is based on the shape. Now we remove the ambiguity of the task, and then we can move forward with more accuracy of the task. Now that we know what problem this article is trying to address and the basic method of achieving that goal, we would like to specify the methods being used. In this article, the query strategy called least confidence heuristic is used. The least confidence heuristic is one of the methods that are often used in active machine learning, where the learner compares the data by the labels with the highest probability, and then chooses the data which this probability is the lowest. For example, let's say that there are two data points D1 and D2. With point D1, the highest probability is 0.9, which is label A, and for D2, the highest probability is 0.6, which is label B. In this case, by the least confidence heuristic, we choose D2. We infer that D2 has the most information that we want, and this is true for removing the ambiguity of the task, because in this case, D2 has more uncertainty of the classification, which means that if we classify and label this data point D2, we will provide more information to the learner. Also, the article uses a very special heuristic, which is removing the need for a separate validation set. For most fine-tuning steps, we need a separate validation set, and so we have to separate the given set into two. However, in this article, they used the simple heuristic of stop fine-tuning when the training loss decreases to 0.1% of the original training loss, and this is proven to be accurate as using a separate validation set in this article. There are mainly two goals that this article is trying to achieve. The first goal is distinguishing causal from spurious features. If there are multiple features in the object, to remove the ambiguity, they want to test whether active learning can help choose the disambiguating examples, which means that they want to choose the examples without the spurious features and only with the causal features. The Waterbirds and the tree-person dataset is used, and the model below is used as the pre-trained model. The second goal is having robustness to distribution shifts. Distribution shifts occur when the training data and the test data have slightly different features. They want to test whether active learning can help the learner to be more robust against these kind of distribution shifts. The dataset and the model used in this experiment are provided below. Also, the experiment is performed with non-pre-trained models to examine whether effective active learning is a result of the pre-training process. Here are the results of the experiments. We can see that in all kind of data sets used in this experiment, there are improvement in average validation accuracy over random sampling. Also, the experiments show that with active learning, the required data set are fewer compared to the random sampling. For instance, with Waterbirds dataset, there were 11% improvement in validation accuracy, and 5 times fewer labels were required to achieve the same final accuracy. This experiment shows a very typical property of active learning. Like I explained before, by using active learning, we can reduce the amount of data that needs to be labeled. Also, because we use the least probability heuristic, we can say that the task ambiguity has been lowered, leading to the increase in the accuracy. Also, results show that all types of uncertainty sampling, or in other words, active learning, outperforms random sampling on iWildCAM dataset. This means that active learning actually causes a positive effect on increasing the accuracy of the pre-trained model. The plot below shows that uncertainty sampling, or active learning, identifies and upsamples disambiguating examples. This means that by using active learning, they were able to choose the data with highest uncertainty, and then by providing labels to them, they were able to remove the ambiguity in the task. Lastly, active learning provided gains when used with pre-trained models. When used with non-pre-trained models, active learning did not show any gain or increase in accuracy. This means that active learning and pre-trained model should be used together to gain high accuracy models. By these results, the team was able to conclude that active learning with pre-trained models select examples that resolve task ambiguity. This leads to an increase in accuracy of the model. Also, they concluded that pre-trained models is the key ingredient in the experiments, so they should be used together with active learning. This is because pre-training yields a better feature space for the active learning, which leads to the increase in accuracy. Next, I would like to talk about the second article, Men Also Do Laundry, Multi-Attribute Bias Amplification. This article deals with fairness in machine learning. Before I move on, I would like to introduce what fairness in machine learning means. Machine learning fairness is the process of correcting and eliminating algorithmic bias, which regards race, ethnicity, gender, sexual orientation, disability, and class. By using machine learning fairness, we can go further and achieve AI ethics, which is very important in current researches. To achieve fairness in machine learning and remove the bias in the machine learning models, we will first have to check if there is any bias in the machine learning models. To do this, we go through a special process called bias amplification. There are several ways of performing bias amplification, but this article specifically deals with multi-attribute bias amplification. Multi-attribute bias amplification means that they deal with features or objects that have multiple attributes rather than only single attribute. In real-life situations, most of the objects have multiple or very many attribute or features with them, so this multi-attribute bias amplification will be a very good way of finding biases in real-life situations. This article claims that current metrics deal with only single annotated attributes and cannot learn correlation with respect to multiple attributes. Moreover, they can give the erroneous impression that little to no bias amplification has occurred, as they aggregate positive and negative bias scores. Also, the current bias amplification metrics lack in an ideal value, which makes them difficult to interpret. They claim that their metric, which is called multi-attribute bias amplification, can have many advantages regarding interpretable models and more accurate bias amplification. For multi-attribute bias amplification, they first had to identify the bias with multiple attributes. The definition can be shown in this figure, where co-occur m, g denotes the number of times in the combination of attributes m and group membership label g co-occur in the training set. This is simply the extension of a single attribute bias amplification equation. Also, they evaluated both undirected and directed multi-attribute bias amplification. The equations on the left is the undirected multi-attribute bias amplification. Here, bias mg denotes the bias score using the test set predictions of m and g. Multi-MALS measures both the mean and variance over the change in bias score, delta, from the training set ground truth to test set predictions. By definition, multi-MALS only captures group membership labels that are positively correlated with a set of attributes. The equations on the right are evaluating directional multi-attribute bias amplification. Here, unlike multi-MALS, multi with the arrow sign captures both positive and negative correlations. Moreover, similar to the directional bias amplification metric, multi with an arrow sign takes into account group membership base rates and disentangles bias amplification arising from the group influencing the attribute prediction. This article claims that the proposed metric has mainly 3 advantages compared to the existing metrics. The first advantage is that this metric accounts for co-occurrences with multiple attributes. If a model, for example, learns the combination of 2 features A1 and A2 are correlated with G, it can exploit its correlation, which leads to bias amplification. The second advantage is that the negative and positive values do not cancel each other out. Existing metrics aggregate over the difference in bias scores for each individual attribute. This means that the negative values and the positive values will sum up together and cancel each other out. However, because this metric chooses to use multiple attributes together, and the co-occurrences and the correlation between those attributes account for independent numbering and values, which means that the scores would not sum up and cancel each other out. The last advantage is that the proposed metric is more interpretable. They claim that there is a lack of intuition in the current metrics as to the ideal bias amplification value is small. However, they claim that their metric has more interpretability compared to the current metrics. Here are the results and analysis of the bias amplification. We can see that more bias arises from multiple attributes, and raw differences collapse individual attributes, but they still survive in multiple attributes. Also, bias amplification is not uniform across attribute groups. After the analysis of their bias amplification method, they move on to bias mitigation. This is because, in order to achieve fairness, they should go farther than just finding the bias, but also to eliminating the bias itself. They benchmarked 5 mitigation methods. The baseline is oversampling, which is greedily sampling to balance single attributes. And then they selected 4 popular strategies that have been evaluated for single attribute bias amplification metrics, and then extended them to fit the multiple attribute bias amplification method. By this experiment, they concluded that mitigating single attribute bias amplification is not enough. This means that multi-attribute bias amplification is needed for a proper and effective mitigation of the biases. Also, the best mitigation method is dataset dependent, which is quite trivial, and the best mitigation method is also metric dependent. The article concludes with claiming that the proposed metric, multi-attribute bias amplification, illustrates the need to consider multiple attributes when measuring bias amplification. They also claim that multi-attribute bias amplification provides a better characterization of the extent to which a model introduces bias from training to prediction. Today, I reviewed 2 articles regarding the topics in machine learning, which are active learning and fairness. Thank you for listening to my project presentation.